Welcome to the Slope Fields podcast. Sorry it took me a little second there to get started. It's just that I didn't realize that I hit I was waiting for the record button to come on. It had already come on. All right, so initial value problems and differential equations can be illustrated with a slope field. Slope fields are mostly used as a learning tool. They can be done in a computer or graphing calculator, but we can also draw them by hand, simple ones by hand. And slope fields provide a picture of a function that you can't necessarily integrate. So sometimes all we have is a differential equation, and we can find the slopes, and we can gather, hey, what's the equation that has this as its derivative? Because we can't integrate it. And even the calculator can't integrate it. But we can see a picture of it. So slope fields, a differential equation gives the slope at any point, x, y. This information can be used to draw a small piece of the linearization at that point, which approximates the solution curve that passes through that point. Repeating that process at many points yields an approximation called a slope field. So we're plugging in for x, and we're getting the value, the slopes, and then we are just graphing all of those slopes. So we're going to graph the family of functions that solves the differential equation dy dx equals cosine x. All right, so we're going to construct a slope field for the differential equation dy dx equals cosine x. The slope at any point 0y will be cosine 0 equals 1. The slope at any point pi y or negative pi y is going to be negative 1. The slopes at all the odd multiples of pi halves will be 0. And the slope is 1 along positive and negative 2 pi. So notice this has to deal with the values for cosine at different points. Different x values, and you notice the wave pattern here. Well, it's going through 0 and it's coming up, and then we have this relative max here, and then if we go the other way, we go the other way, I missed my point, and then the function comes back up. I cannot seem to draw this well on the smartboard. But I think even with this kind of really mediocre drawing here, I think you can see what function this is, just kind of following along here with the values. And this is sine. And notice that sine is the function whose derivative is cosine. So this one we could integrate. But even by looking at the slope field, we could see what function it is coming out. And notice that all these lines are just translations. I can't seem to move that without moving the whole screen. Vertical translations. So there would be +1, and we can move it down here to -2, right? Because those won't matter, because when we take derivatives, those disappear. Sorry for the crooked line. But I think you get the idea. It didn't turn exactly where it should have. It should have turned a little bit faster. Of course, now it's in 3 pieces. But there you go. Let's look at another one. And then I'll do some from scratch. So here we have dy dx equals 2x, or y prime equals 2x. Notice here that over here, this is the x value. I just want to make sure this was clear. This is the x value. This is the y value that I get, and it's also the slope. So the y value gives me the slope, if you will. It's really the dy dx. So when we plug in, because it's equal to the slope. Maybe I should write it like that. Maybe that's even better way I can say it. So if you think about it, this is slope equals cosine x. So I plug in for x, and when I solve, I get my slope. I think that made it, that's a clear way to say that. All right, so here my slope, I'm going to write that. Slope equals 2x. What's my slope? I'll just plug in for x and I'll find it. So notice here that I have these y values, 0, 1, 2, 3. Notice that the x's and the y's are the same, because the y is immaterial. There's no y's in this equation. There's a y prime, which is a dy dx, but there's no y. So it doesn't matter. All through here, no matter what y is, if x is 0, then y prime, the slope is 0, right? Because if I plug in 0 for x, I get 0. And no matter what y is, and there's not every point listed here, if x is 1, then the slope is going to be 2. And whatever, doesn't matter what y is, whenever x is 2, the slope is going to be 4, and so forth. Whenever x is negative 1, the slope is going to be negative 2, because that's what I get when I plug in. All right, so here we can see these graphed. So notice that here at wherever x is 0, regardless of what y is, we have a horizontal slope. And notice that it gets steeper and steeper as x gets larger and larger. And then if x is positive, our slopes are all positive, and if x is negative, our slopes are all negative. And you can see that pattern coming out. It looks like a parabola. Right? So no one expects you to be out, because you're drawing these little short lines. So it's kind of hard to be absolutely perfect with your slope, but it should be steeper. So if one line is supposed to be a slope of 1 and the other is supposed to be a slope of 2, well, 2 should have a steeper slope than 1, right? And if it's 0, it should be a horizontal line. And if it's undefined, it should be a vertical line. So it's more degree in terms of your slope field. Is the degree correct as you go across? Are you showing it's getting more steep? Right? Right, and notice here that we have the family of functions. I didn't mention that. So y equals x squared. If I shift it up, I have y equals x squared plus 1. If I shift down, I've got y equals x squared, maybe minus 3. And here we can see that, yeah, that really is it, because this one was one we could actually integrate and find the equation. So if we move dx, multiply both sides by dx, and then integrate, we have y equals x squared plus c. And that's exactly what we see in our slope field. So if we know an additional condition, such as 1, negative 2, then we could sketch the curve. So the red curve that's drawn in there is for 1, negative 2. So in other words, my y value is negative, my y value is going to be negative 2. So if we, excuse me, it's negative 3. If I have to plug in, my goodness. I have to plug in for x and y and solve for c. So if I have negative 2 goes for y equals 1 squared plus c, negative 3 is equals c. Sorry, I just lost my train of thought there. So my general solution is y equals x squared plus c. The particular solution is y equals x squared minus 3, because we solved for c. Right? So when we have an x and a y, we have to plug those in and solve for c. Neither one of them is c. All right, so here we want to draw a slope field. I don't know if I included this picture. I didn't, but I didn't include this slope field. I don't know why I didn't, but I didn't. But I'll go through it anyway, and then I can always add this in class if you'd like. So if we're drawing a slope field, it's because it's basically the same question over there. So if we draw a slope field for the differential equation, so this is the question that goes with the problem we just did. Dy dx equals x squared. In general, the slope field of the differential equation y equals dy dx is defined for every point xy in the domain of f. We're going to assign a small piece of tangent line with a slope f prime xy equals dy dx. In other words, our function equals slope. So when we plug in and we evaluate, whatever answer we get, field at this point will be a small piece of tangent line with a slope that matches the tangent to the curve that passes through the point. So in this case, if we plugged in at the point 1, 2, the slope would be 1, because 1 squared is 1. Actually, no, this is a different equation. I'm sorry, this is dy dx equals x squared. We had dy dx equals 2x. This is a different equation, and I don't have the slope field here. I don't know why. Or a place to even draw my slope field. So maybe at the end, if I have a little time, I'll do this problem so that we could see this one. I keep thinking that I have this one in here somewhere. We'll find out. So notice that here, there's no place to plug in for y. I'm just plugging in the x's. So no matter what y is, everywhere along those x's, we're going to have these slopes. And I know I probably didn't plug it in. Just try to draw a slope like that. So it's not that easy to draw a slope of 25, right? Just make it steeper than 9, all right? And make it steeper than the ones it's supposed to be steeper than. I am going to do these couple here. Why did I choose dy dx equals 2y? I just did that one. All right, let's change it. I was adding some new problems, and I added one that I just already have. All right, so, all right, let's do the one then that was over here. We can do that. Let's do x squared. And then we will have done the one that I have listed there. Ha. All right, so dy dx equals x plus 1. I'm going to make a little... All right, so I'm just going to write in x, and I'm going to put dy dx or slope. And I'm just, for every y, I'm going to put in, I know I'm going to go all the y's for that x. All right, so I'm going to plug in, so I've got 0, 1, 2, and 3, and -1, -2, and -3. So I'm going to plug all those in. So if I plug in 0, 0 plus 1 is 1. If I plug in 1, 1 plus 1 is 2. If I plug in 2, 2 plus 1 is 3. If I plug in 3, 3 plus 1 is 4. If I plug in -1, I'm going to get 0. If I plug in -2, I'm going to get 1. Why is this line so crooked? Is anyone else bothered by how crooked this line is? Let's move that over. There we go. And if I plug in -3, I'm going to have... Sorry, -1. -2 plus 1 is -1. And -3 plus 1 is -2. All right, so on the left we have our x's, on the right we have our slopes. I'll do the best I can. Sometimes I end up redoing these because I'm not satisfied with my slopes. I'm going to start with the zeros because I'm pretty sure I can do that. All right. So all along -1, my slope is going to be 0. Right. Maybe I got a relative maximum in there. And I'm going to work my way up so that I make my slopes each time a little bit more steep. I'm going to do -2, which has a, excuse me, I'm going to do 0, which has a slope of 1, and then I'll do -1, which has a slope of, -2, which has a slope of -1. All right, so slope of 1, I'm going to call that a slope of 1. That's not too bad. So all of these have a slope of 1. Okay. And then -1 should look pretty much the same, except go in the other direction. All right, so that looks to me like 1 and -1. All right, so now let's do 2 and -2. It should be steeper. All right, so at 1, I've got a slope of 2. It should be steeper, so that looks steeper. That looks steeper. And I'm trying to keep them all the same so that it's clear that they're all a slope of 2. Of course, one slope decided not to hit the right point. No. Let's just redo the line, since the line does not want to move. It'll stay there. You won't have that problem. You won't have to worry about orienting your paper. All right, so now I'm going to have the same slope here, but it's just going to be negative. So it should be steeper than -1. All right, so now I've done -2. All right, so now I've got everything. Now I'm going to do 2. 2 is a slope of 3, so that should be steeper. And -4, that should be steeper. But I don't want to make it vertical. Wow, that, I don't know how to call that steeper. And actually, let me redraw these ones. I've maybe made this one too steep because I'm getting a hard time making the 3 and the 4. Maybe just a little more steep. All right, let's try that. See, now it looks like my 1 to me. So you can see there's a little bit of trial and error. If you make a table also, especially on the AP test, at least they'll know what you were trying to graph. I can't say I do these perfectly. All right, I'm just going to go with it. There we go. I'm going to call that good. And this one more. It's a little bit more. I think it's these ones up here really got to be a little too steep, I think, too quickly. And so did these. I don't know. As I go along, it seems like I make them steeper. So, but you get the idea. Okay, there we go. I'm satisfied with that. You can see it looks like it's getting steeper, and I wrote the slopes here, and I was trying to get them steeper. And we could kind of see our function here. Looks like I might have a parabola again. I kind of see a U shape. It's getting steeper on the ends there, right? Maybe it's shifted a little bit, right? On this one we can integrate. So if we integrate x plus 1 dx, right? This would be dy equals. That would be y equals x squared divided by 2 plus x plus c. So there you can see we have a parabola, and it is shifted a bit. All right? Because of that plus x. All right, let's try the next one. Let's see if I can do a little bit better with my slopes. All right, so I'm going to make my table. I think I made the 1s too steep, and then it made it hard to make the 4s steeper. So try not to make them too steep so that you can make the other ones look steeper. All right, so I've got x and dy dx, and dy dx is slope. So I have the same values. If I plug in 0, I'm going to have 0. If I plug in 1, I'm going to have 1. If I plug in 2, we're going to have 4. And if I plug in 3, we're going to have 9. So I really got to be careful on this so I can get a slope of 9, or what looks like 9. If I plug in negative 1, I'm going to have 1. If I plug in negative 2, I'm going to have negative 2. And if I plug in, negative 2, 4. And if I plug in negative 3, it's a slope of 9. All right, let's see if we can do this. So I like the zeros. 0, 0, 0, 0, 0. All right, and so 1. I'm not going to get this so steep. 1, 1, 1, 1, 1, and I'm going to have 1 also at negative 1. 1. Notice all of my slopes are positive. So this is an increasing function everywhere. Yeah, now this one looked crummy. Now I took out the one that looked pretty good. Still looks crummy, but that's okay. And then the 2 should be steeper. And then the 3 is going, and then the next one's going to be really steep. So I'm going to draw this one steeper. As steep as I can make it, not make it look so vertical. Make it look vertical. And then this one kind of in between those. And like I said, put a table of values. So in case one line like this, you can always redraw it. But in case one is just giving you grief, at least they know the slope you were intending to graph. And then this would be the same thing. So this would be really steep at 9, really steep at 9. That's not so much steep. I swear, I'm trying to draw it one way, and I swear this pen draws it another way. No, that should be more steep than that. Supposed to be like twice as steep. Not that steep. Well, I think I'm doing a better job on this one. So draw your least steep and your most steep, and then work your way in between those. There we go. So again, we can see, and you know, I see an SE-shaped function that's increasing. Right? We can integrate this one. So dy equals x squared dx. We integrate both sides. Y equals x cubed divided by 3 plus c. And that's what I see. I see x cubed. Do you see x cubed? Hopefully you see x cubed. So our slope fields here kind of give us a hint on the function. So begin looking at them as functions translated all over the place. Translated up and down, not right and left, but up and down. So you can kind of envision these functions. We're going to match the slope fields with the differential equations. Figure out a possible equation using the pattern of slopes. You can find the differential equation for the possible equation using our methods shown. Right? Some of these we can integrate. Matter of fact, all but one we could integrate. All right, so let's integrate them. And let's look at the pattern first. We'll write down the pattern that we see, and then we'll integrate. I think I'm going to go to D right here. I think we can all clearly see a circle hanging out there. We probably can figure out which one of these is the derivative for the circle, because we saw it so much with implicit differentiation. This one here kind of looks like a parabola to me. So just by figuring it out, I see an exponent. I kind of see, notice here, I see a horizontal tangent, don't you? Right at 0? Because look, the points are going either towards it or away from it. Maybe this is an exponential equation. So I'm not guaranteeing these are these things, right? But that's what I see. To me, I have a harder time with A. Looking at that one, I got something really steep and then it comes up. To me, that's the one that doesn't stand out as much. I think that maybe C is an exponential, and I think maybe D is a circle, and maybe B is a parabola. A just doesn't hit me as much as the other three do. Let's differentiate, let's integrate, solve these differential equations, the ones that we can. So we're going to solve 1, 2, and 3. And process of elimination, we will figure out 4. So you can always do it that way when you have a problem like this. All right, so dy equals 0.5x minus 1 dx. We'll integrate both sides. I lost my 0.5 there. I'm still losing my 0.5. By the way, don't pull that 0.5 out unless you separate this into 2 different integrals. If I leave that as 1, that's not good, because the 0.5 only goes with the x, not with the 1. So notice I've not pulled out any constants because I've not separated these. I've just integrated. All right, so I have y equals, this is going to be 0.5x. Actually, I'm going to write that as 1/2. I really don't like the 0.5 that much. It's simpler for me to simplify without the decimal in there. 1/2 x minus 1. All right, so now I've got 1/2 x squared, and now I got to divide by 2 minus x plus c. So y equals 1/4 x squared minus x plus c. We do have a parabola. I think 1 goes with b. So I'm going to put a big B there. I think 1 goes to that one, because that looks like a parabola to me. Do you see the parabola? And we're shifted to the left. Notice, do you see how the slopes are shifted? How the center of the parabola, the vertex, is over 2 now. And so that means we're going to have a negative x, or I'm going to be adding something negative in terms of a constant to my parabola. That's what will shift that thing to the left. I mean to the right. To the right. All right, let's look at the next one here. So I'm gonna change that to 1/2. And I'm going to move the dx over. So dy equals 1/2. Oh, oops, excuse me. Well, y dx. I've got to divide by y. So if I move the y, let's just do this one again. Let's just move everybody at the same time. So move the 1/2 y. So this was, let me just rewrite it. dy dx equals 1/2 y. The y's got to move because the dy is in the numerator there. And I need the y on the other side. So we're going to multiply by 2y. So I'm going to have times 2y dx. And over here I've got 2y dx. I'm trying to multiply. So if I multiply both sides by 2y and dy dx, now I don't know where else to write here, that over here, this will cancel, so I'm going to have just a dx. On the other side, the dx will cancel, so I'm going to have, oh my goodness, I don't want 2y, I want 1 over 2y. This is what I get when I don't have enough space. All right, where am I going to solve? I'm going to solve this one I'm going to solve it up here, because I have like no space. dy dx, I'm going to first rewrite it. Then I'm going to write the things next to one another so I don't write them upside down. 1/2 y, and now we're going to multiply by 2 and by dx. Let's just move those guys first. So now I've got 2, so then I'm going to divide by y. 2 dy equals y dx. Everyone agrees that's okay, right? All I've done is moved the 2, and moved the dx. Now we'll divide by y. 2 over y dy equals dx. And I think I'm wrong about where I guessed exponential, maybe not, where I guessed exponential, and now I'm thinking it's going to be something different. All right, so now we'll integrate this. Integrate. This is going to be, no, actually, I take it back. It's going to work out. I'm not wrong. When all is said and done, I think this is going to be an exponential. So this is going to be 2 natural log of y is equal to x plus c. And I want to solve for y, so I'm going to divide by 2. Probably should have maybe left the 1/2 over there. So now this is natural log of y equals 1/2 x plus c. Doesn't really matter the c. Half of c is still, half of a constant is still a constant. And now I'll exponentiate, so I'm just going to put an e under here. And I'm going to put an e over here for the whole thing. And so now this is going to cancel. This is going to be y equals, and this is going to be e to the 1/2 x. And that plus c is going to become times e to the c, and we know that could be rewritten as a. So I was right. That's the exponential. So this one is c, the exponential. So the first one was b here is what 1/4 x squared minus x plus c, and c is y equals ae to the 1/2 x. So it's a lot easier to figure these out once you can solve the differential. So now we've got, and so that's 2 here. 0.5y is the differential equation that goes with c. Now you could also, what if you can't? I'll show you another way on the one we can't solve, which is 4. Even though process of elimination, there's only going to be one term left. All right, this one here, we're going to multiply by y. I've got, and multiply by dx. I've got y dy equals negative x dx. We integrate. We're going to have y squared divided by 2 equals negative x squared divided by 2 plus c. Let's multiply everybody by 2. Move the x squared over. Hey, it's x squared plus y squared equals c. That's a circle. So this 3 here goes with d, which means process of elimination. The one that didn't stand out to me is the one that we couldn't solve anyway, which is a. All right, so we can't solve that because they're added. There's no way for me to move anybody over. But what we could do is we could look at the slopes. So for instance, if I can't do anything else, I can plug in the x and the y values and see what matches the slope. So for instance, if I plugged in 1, negative 1, right, I'm going to circle that slope piece. See that slope piece right there? All right, so dy dx equals 1 plus negative 1. Well, that's 0. Look at that, matches. And what if I add 0 plus 0? That matches. So notice, even though I can't figure out the equation that goes with that one, because it's not a separable one, all those slopes, those 0 slopes, match exactly what we'd get if we plugged in for x and y. So here, the one we can't solve, we can figure it out by using our slope field. All right, so that one is A. So even though I can't solve it, I know that that has the right slopes. Right? Anywhere where I'm plugging in the slopes, where they're opposites of one another, I'm getting 0 for a slope. And that matches that slope field. Okay? So that's how you can solve this one. Oh, my slope field podcast is taking longer than I thought. All right, I think I'm probably going to end this right here. I have a few more slides, and then I'll pick up with the second slope field podcast. All right, bye.